Okay, so in this video, I want to look at solving inequalities and primarily polynomial functions because that's what we've been talking about. But we can look at other functions like rational functions or square root functions and apply the same principles of polynomials and still be able to answer the question of the solution set of this inequality. So when I see an inequality, like this. I often think about, well, what if it was just an equal sign, right? Let's just figure out what's the equal sign, and then we can figure out, are we greater than that value or are we less than that value? So I'm sort of going to temporarily ignore this and just focus on what if this were a function? What if it were like f of x equaled, x minus 3 squared times x plus 2? Well, we spent some time and you looked at some practice yesterday that if you were to sketch this, you would focus on end behavior first, and end behavior meaning that this overall is a positive function, right? There's nothing in front there. It's a positive function. So we know that a positive function, all positive functions, will land us up in quadrant 1. Right, so I know it has to end here, and then I'm going to look at the local behavior of the x-intercepts, one of them being at 3, one of them being at -2. And the behavior at 3, because the multiplicity of that exponent is even, I should use yellow or a different color. Since it's even, that means the behavior at 3 will have an even behavior. And since the multiplicity of the factor x plus 2 is odd, particularly 1, we'll know that's going to intersect there. So when I draw my graph, as if I were to be sketching a graph of this function, I know it's up here. The end behavior, it's a positive function. We touch and go. We're up here for a while, and then eventually we go back down. And certainly I know that the power function, if I were to have asked this, I know I don't, is a cubic function, and the overall behavior looks like a cubic function. So I know that I'm in the right frame of a sketch to represent this behavior. Now, I don't necessarily need to know what this y-intercept is. As a reminder, we don't really know what the highest point or the local maximum is, and that's okay. I'm just getting a sketch of the behavior, because now what I'm going to do, let's maybe pick like maybe this color or this color here. So now what I'm going to do is focus on where are things that are greater than 0. Well, things that are greater than 0 will be above the x-axis. That's where the positive values go. So I want to capture that, but I need to capture that based on when it's happening. And when it's happening is an x value. So when is it happening? When is it above? Well, it's certainly above, like starting when x is -2, but not including -2, and going all the way here to 3. So I want to start at -2 and let x run in between -2 and 3, but strictly between those 2 points. I'm not going to make them equal. I'm not going to put underlines there, because I don't want less, or I don't want greater than or equal to over here. It's just strictly greater than. And then I also have 3 and beyond. So x is greater than 3. So that algebraic statement gives us all of the x's that are satisfying this inequality. Now, some of you might know interval notation. And interval notation really just focuses on sort of the endpoints of this interval and its behavior. So if I know I'm starting at -2 and I'm going up to 3, then I can just kind of keep track of those. So I'm saying, okay, I'm going to start at -2 and I'm going to go up to 3. And it's assuming those, not assuming, that we're conveying that they're all x's that fall within that. Now, it gets a bit confusing because it looks like an ordered pair, but don't worry, it's not. It's not in the context here. It's not an ordered pair. It's an inequality. Now, the parenthesis means something. If I wanted to equal those values, then I would have made it a hard bracket, and I would have distinguished that interval with a closed bracket or a hard bracket. But this open interval tells me that it's strictly in between those two. Now, if I want x also greater than 3, we focus on 3 as the lower point, and since it goes on forever, we'd say infinity is the upper endpoint. So if I ask very explicit interval notation, I would say negative 2 to 3 union the interval 3 to infinity. That's one way to express all of the x's. But guess what? So is this. And we should be flexible between the two, and just realize the equivalency of them. Okay, let's look at number 2. So on number 2, I really, really wish I could be here in person to say, don't do, a very common mistake, right? Don't do any division. Set it equal to 0. That should be your first step, right? Set it equal to 0. So rather than maybe dividing by an x squared, which that may have been your instinct, don't tell me that. Let's subtract 9x squared. So now I've set it equal to 0. I can factor that x squared out, and it looks a little more familiar to what I was thinking about during the inequality or during the polynomials. And that's a difference of squares, so I can factor further. And so I'm going to look at this first as a function, right? Let's look at it first as there's a function here, like that has 3 distinct zeros, one at 0, one at 3, and one at negative 3. So when I come over here and I know that 0 is a point I want to look at its local behavior, 3, oh, maybe over here, oh, maybe not. Sometimes my pen doesn't like to do what it needs to do. There it is, x equals 3, and also x equals negative 3. And overall, this function, the way I have it set, is positive, which means its end behavior is up here. So then I know it's gonna it's gonna start somewhere up here, has to approach 3, and again, just to highlight, like literally one more time, the multiplicity of the factor that gives us 3 is 1. So it's gonna it's gonna intersect through like a linear function. The multiplicity at negative 3, that factor is also 1, so it's going to intersect. And the even multiplicity at the squared means at x equals 0, the behavior will be quadratic or parabolic. So, and then let's go ahead and get this graph. So I know I'm starting up here. I got to cut right through 3, and eventually I go down, but I'm going to have to approach at 0, and it's a bounce. I go back underneath, and I go right through that. So I'm sort of looking at this W shape, and that's really indicative of an overall fourth degree, right? My power function is going to behave like a fourth degree. Now, again, I don't necessarily need to know the graph to answer the question about where are the numbers that are less than 0, and so those exist down here, and I need to keep track of the x's. When is this happening? So the x's, and again, it's strictly less than, right? It's strictly less than. So those x's begin here at negative 3. And the first thing I can do, I guess, is just do just an algebraic sentence that negative 3 is less than x. Now, technically, it's less than 0 because at 0 it's equal to 0. I don't want to include that point. I want to think about it as an open circle, and then from 0 is less than x is less than 3. So I got these two distinct or disjoint intervals. If you want to put it into interval notation, you certainly can. By just keeping track. Well, I'm going to start at negative 3 but not include negative 3. I'm going to go up to 0 but not include 0. And then union this interval starting at 0 but not including 0 and up to 3. Now, you probably already noticed that's a pretty cumbersome and complicated way. We have to throw out that 0, right? But it is important because if we're strictly less than, we want to indicate only the x's where that would necessarily be true. Okay, and so let's go ahead and solve number 3 on this video, and that'll be a good ending point for this first video. So again, just looking at it as a function. If I just treated this as a function, I have 1, 2, 3 distinct zeros, and its overall behavior, if it were a function, would be positive because there's no negative value that would influence the overall behavior of this particular graph. So I'm going to keep track of that as my end behavior. Again, a positive function is going to end up here. And my zeros would be at 0, x equals 0. At 5, I'm going to really space this out because I'm noticing that there's also an at 4. And again, not drawn to scale at all. X equals 4. So again, one more time, I like that highlighting effect at x minus 4 squared. So the behavior at that 0 should be even. At the cubic one, it should be odd and should be that squiggle. And then the linear one would just go straight through. So again, our overall behavior is positive. So we know we're ending in the first quadrant. So that's where I'm going to begin my graph. And at 5, I got to do the squiggle. So I'm coming in approaching 5. I'm doing this. Well, I'm going to try to do the squiggle if my pen cooperates. There it is. I can't go down too far because at 4, I got to do a little bounce. And then at 0, it's straight through. So again, it's sort of a W shape or U shape with a, and I'm thinking, well, that's indicative of an even function. And that's exactly what we have, right? An even function, the power function is equal to x to the 6th if I were to expand all that, right? So that's great. And I want, where is it positive? Where is it greater than or equal to 0? And so again, looking at just highlighting this region up here and keeping track of those x's. When do the x's give you a value above this, right? I lost my highlight, but that's okay. There it is. So I definitely can go forever on the left. And this is the first time that I'm greater than or equal to. So I can equal 0. So that's going to change my bracket when I write that interval notation. But to start with, I know that x could be less than or equal to 0. I know that x could be greater than or equal to 5. And there's a real sneaky point. X could also equal 4 because that's right there, right at that spot, it actually equals 0. So those three combined would be one way to express all x's. Now, interval notation, how do you show it's less than or equal to 0? Well, you start at negative infinity, you go up to 0, and you put that closed bracket. Now, it's weird to have a point in interval notation, but technically you could. You could say start at 4, end at 4, and include both points. So it's a very complicated way to say x equals 4. And then union 5 up to infinity. And so right now, we may have different backgrounds on interval notation. And so if you're not, completely 100% proficient in interval notation, I'm okay, but we need to get there, right? So make sure you ask questions so that you can take your algebraic expression and be able to write its equivalent interval notation form.